Okay, hello calculus class. This is our summer video series number 5, right? Video number 5. Okay. So in the previous video, we went over how to find some limits, um, doing direct substitution, and also some limits by rationalizing the numerator. Okay, so today we're going to talk about a few different things. And then after we do that, we're going to look at a whole bunch of different limits and make sure that you're comfortable taking the limit. First off, one of the things that we talked about in the previous videos was a situation where the limit does not exist. Now, there are 3 scenarios under which the limit will not exist. Okay. So the first one we've already talked about, and that's when the limit from the left is not equal to the limit from the right. In this case, the limit would not exist. So to give you an example, okay, if we're looking at, let's say the limit as x approaches 2, right, and we're looking at a function that looks like this. Okay, so this limit would not exist because the limit from the left is equal to 2, right? The limit as x approaches 2 from the left is equal to 2, but the limit as x approaches 2 from the right is equal to 3. They're not the same, therefore the limit does not exist. Okay, another case where the limit does not exist is when we have what we call oscillating behavior. Okay, so for instance, if I had f of x equals sine of 1 over x, okay, if we actually look at that graph, let me see if I can pull it up on my calculator. I have it on the calculator, sine of 1 over x, and I just made sure that I'm in radian mode. And I made my window relatively small just so we can inspect it, okay? And what I want to do is I want to look at the limit as x approaches 0 of this function, okay? So let's see what's going on as x approaches 0. So if we look at this graph, this is kind of a really weird graph. This is what we call oscillating behavior. And the best way I can explain that is kind of like if you took a yardstick and just like twanged the end of it. Okay, it would kind of go like right. That's oscillating behavior. It's oscillating back and forth, back and forth, back and forth, back and forth. Okay, and that's what's going on here. As we're approaching 0, it's sort of just going up and down, up and down, up and down, up and down, up. Right? It's kind of like that's oscillating behavior. Okay. And when we have oscillating behavior, the limit actually does not exist, right? If we look at this, if we look at where, let me see if I can zoom in on that just to make it more obvious. Okay, so there you go, okay? If we look at where x equals 0.0 or 0.1, which is just like really right here, right? Coming from the right, right? So what's happening? F of x is actually negative. F of x is down here as we get close to 0 from the right. But as we get close to 0 from the left, f of x is actually up here. I don't know what the value is, but it's positive. So these two limits are actually not going to exist, although it looks like they're approaching the same value, right? So in that case, it's really kind of a weird thing. And it's just best just to memorize that if it's oscillating, the limit does not exist, okay? Okay, so that's another case where the limit does not exist. Okay. Okay. The third scenario where the limit does not exist is what we call unbounded behavior. And this can sometimes get a little confusing just because of the vocabulary that we use, right? So sometimes when, let me just draw this first. Okay, so let's look at an example of f of x equals 1 over x minus 2 squared. Okay, so this is actually going to have a vertical asymptote at x equals 2, which means we're going to approach that value but never actually cross it. Okay, so my curve is going like this. Okay, so when we look at this, if we look at the limit as x approaches 2 of that function, okay, as we approach 2 from the left, okay, so we're going from this direction, right? What's y doing? Y is actually approaching infinity. And as I approach 2 from the right, y is also approaching infinity. So in this case, the limit from the left is actually equal to the limit from the right, okay? But it's approaching infinity, and infinity is not a real number, okay? Infinity is a behavior. So if it's approaching infinity, just think about the words. How can we have a limit? It's not approaching a finite number. It's not approaching a number that we can identify as a number. It's approaching infinity. Well, what number is that? Is that 5 bazillion? No, because infinity could be 5 bazillion plus 1. Is it 5 googolplex? No, because it could be 5 googolplex plus 1, right? So infinity in itself is unbounded, which means infinity in itself has no limit. So when we have something like this, we could technically say that the limit as x approaches 2 of f of x, we could say that it equals infinity because it does. But by the nature of that, the fact that it equals infinity actually means that the limit does not exist. So both of these are actually correct in this case. In the other two cases, the limit just does not exist. The limit doesn't exist. There's no finite number that I can identify in number 1 or 2. In number 3, the limit is actually infinity, which means it does not exist. Okay? So I prefer that you state that the limit is actually infinity because that is a very different situation than at case 1 and 2. However, that means that the limit does not exist there. Okay? Okay, so let's just review some of the methods for analyzing limits. Am I spelling that right? There we go. Okay. So our first method, the first thing we want to try is what we call the direct substitution. And in this case, we are just substituting the value into the equation. Okay. Um, then we're going to use our properties of limits that we learned. Okay. In other words, the limit as x approaches 2 of 3x squared times 4x. Well, that's the same thing as the limit as x approaches 2 of 3x squared times the limit as x approaches 2 of 4x and so on, right? So we learned a whole bunch of those, okay? Another thing that we're going to try and do is factor and cancel if possible. We're going to try multiplying by the conjugate if possible. Okay. Well, one of the other things that we can do, we have two special trig limits that are important. So sometimes we just have some special limits that we memorize, right? So one of the special trig limits is this one, the limit as x approaches 0 of sine x over x. Well, that is always going to equal 1. Okay, that will always equal 1. So that's one of the limits that we have to memorize. We're not going to prove it, but you do have to memorize it. The other one is the limit as x approaches 0 of 1 minus cosine x over x. This will always equal 0. If I look at either one of these limits, okay, if we did a direct substitution, right, I would get sine of 0 over 0, and sine of 0 is 0, so I'd get 0 over 0, right? So we know that's a problem. Here I'd get 1 minus cosine 0 over 0, which is 1 minus 1 over 0, which equals 0 over 0. So both of these are going to be a problem in themselves. So we can't do a direct substitution. So we're going to call this one of the properties of limits, these two rules, because I can't factor, I can't multiply by the conjugate, okay? So I get this 0 over 0. I don't know if we mentioned it in a previous video, that 0 over 0, or if we get infinity over infinity, these are called the indeterminate forms, okay? The indeterminate, okay? And knowing what it's called is really not that important, but just know that it is a problem. If we get 0 over 0 or infinity over infinity, that is a problem, okay? There's another method that we are going to learn later when we learn derivatives, and that's called L'Hopital's rule. So we're gonna skip that for now, um, but it is a method that we'll learn later. Okay. So let's just look at a few limits and see, make sure that we're okay before we move on. How about the limit as x approaches 2 of 3x squared minus 5x plus 4? Okay, so here we're going to just do a direct substitution. Right, so this is going to be 3 times 2 squared minus 5 times 2 plus 4. And that's going to give us 3 times 4 minus 10 plus 4. So that's 12 minus 10 plus 4, which equals 6. Okay, so that's really, really quick and easy. Okay, how about this one? The limit as x approaches e, you didn't think we were finished with e's, right? Of the natural log of x over 3x. Well, this is another direct substitution. We get the natural log of e over 3e. And who remembers what the natural log of e is? 1. So we get 1 over 3e. And that's our answer. How about the limit as theta approaches pi over 6 of sine 2 theta? Well, that'll be sine 2 times pi over 6, which is sine pi over 3. So we've got to remember our unit circle, right? Pi over 3 is right here. So that's 1/2 square root of 3 over 2. Sine is the y value. So this is equal to the square root of 3 over 2. Okay. Let's look at the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 6x plus 8. So if I direct substitute, I'm going to get 4 minus 12 plus 8. That equals 0. And on the top, I'm going to get 4 plus 2 minus 6. Well, that also equals 0. So here we have a problem. So what can we do about it? Yeah, let's go ahead and factor, right? I can't do a direct substitution, so let's see if we can factor. So we're going to factor this x plus 3, x minus 2 over x minus 4, x minus 2. Well, that's great because my x minus 2's are going to cancel. So we have the limit as x approaches 2 of x plus 3 over x minus 4, which equals 5 over negative 2. There you go. Okay. Okay. How about this one? The limit as x approaches negative, I'm sorry, x approaches, yeah, x approaches negative 1 of the square root of x plus 2 minus 1 over x plus 1. Okay, what are we going to do for that one? Because if I put a negative 1 in here, I'm going to get 0. And if I put a negative 1 up there, I'm going to get a 0. So we have 0 over 0 again. Okay, we're going to rationalize the denominator. I'm sorry, rationalize the numerator. Sorry about that. We've got the square root of x plus 2 plus 1 over the square root of x plus 2 plus 1. So we multiply by the conjugate, and that gives us the limit as x approaches negative 1. Okay, we're going to FOIL this out again, so we get x plus 2, and we're going to get minus 1 on top. And on the bottom, we have x plus 1 times the square root of x plus 2 plus 1. So when I FOILed, remember what we talked about in the last video, right? Square root disappears. Here I get plus root x minus x plus 2, and we get minus root x plus 2. And then we get minus 1. Okay, so this is the limit as x approaches negative 1 of x plus 1 over x plus 1 times the square root of x plus 2 plus 1. Okay, my x plus 1's are going to cancel. So we have the limit as x approaches negative 1 of 1 over the square root of x plus 2 plus 1, which equals 1 over the square root of negative 1 plus 2 plus 1. That's 1 over the square root of 1 plus 1, which equals 1 over 2. Okay, these can get pretty tedious, but it's all math that you know how to do. Okay, let's look at this one. Here we have the limit as x approaches 0 of x over 1 over 4 plus 1 over x minus 4. Now this one is tricky. If I do a direct substitution, I get 0 over 1/4 minus 1/4, which is 0 over 0. So we need to do something here. Okay, we can't factor, and we can't multiply by the conjugate, but we can simplify it. So let's look at that. Let's multiply by the least common denominator. Okay, so we're going to multiply by, I've got 4 and I've got x minus 4. That's what we're going to multiply by, and we're going to multiply by that on the top and the bottom. Okay, we're simplifying a complex rational expression. Okay, all right, so what's going to happen here? I'm going to write it out, even though that's kind of tedious. We're going to write the whole thing out so you can see what happens. Okay, so what I did is I figured out the common denominator. And basically, the way I think of it is every denominator needs to be represented. It doesn't actually have to be the least common denominator, but every denominator has to be represented. And what's going to happen is these denominators are going to disappear, right? So I'm going to get 4x times x minus 4. And then on the bottom, we're going to get, now we're multiplying everything by that. So we're going to get 4 times x minus 4 over 4 plus 4 times x minus 4 over x minus 4. Okay, I took this, so think of this as being like over 1, right? Okay, so now I've got the limit as x approaches 0 of 4x times x minus 4. And look what happened in the bottom. The 4's canceled there, leaving me with just x minus 4 plus, and now the x minus 4 is canceled, so I'm just left with 4. Okay, so multiplying by that common denominator removed these complex expressions. Okay, we simplified the complex rational expression. Okay, so now we have the limit as x approaches 0 of 4x times x minus 4 over x. Well, that looks like a problem still, doesn't it? Because I've got a 0 in the denominator. Oh, but look, these x's are going to cancel. So now I'm left with the limit as x approaches 0 of 4 times x minus 4. And when I substitute 0 in there, I get negative 16. And that's my answer. Okay, let's look at another one of those. Let's take the limit as x approaches 0 of 1 over 2 plus x minus 1/2 over x. Remember, we're always going to try to direct substitute first. Okay, when we do that, we're going to get 1/2 minus 1/2, which is 0 over 0. So we know we have a problem. Again, we can't factor and we can't rationalize, so we need to simplify this complex expression. So once again, we're going to multiply by the common denominator. So I have a 2 plus x, just represent every denominator, and I have a 2. Okay, we're going to multiply by that on the top and on the bottom. Okay, and that's going to give us a limit as x approaches 0, right? I'm multiplying everything, so this is going to be 2 plus x times 2 over 2 plus x minus 2 plus x times 2 over 2 over x times 2 plus x times 2. Okay, well, let's cancel things out. 2 plus x's cancel, right? So we have the limit as x approaches 0, 2 minus, now here the 2's are going to cancel. So be careful because we're subtracting the whole 2 plus x over x times 2 plus x times 2. Notice I did not multiply the denominator. Make that a habit. Don't multiply the denominator out until you determine that you have to, because most of the time things are going to cancel for us. Okay, we've got 2 minus 2, except that's not a 2. 2 minus 2 minus x. So we have minus x left on top. And down here we have x times 2 plus x times 2. Well, we've got more stuff that can cancel. My x's can cancel. Just be careful about that negative sign. That's the limit as x approaches 0. This is negative 1 over 2 plus x times 2. Now I can substitute that 0 in there, and I get negative 1 over 4. And that's our answer. Okay, we're going to stop there. And you've got some work that you have to do. Um, and then we'll have just one more video for this summer video series.